We keep learning. Welcome to another session in our series of tutorial in R for data science. And in this session, we're going to look at exploratory data analysis, what it is, what it entails, and in exploratory data analysis, just as the name suggests, we are trying to explore the data and to see some hidden relationship in the data. And here we'll use graphics and visualization. We'll also use statistic knowledge, the different domain knowledge to explore the data. So the different domain, whether you're working in health, whether you're working in business, whether you're working in agriculture, whether you're working in transport, whether you're working in IT, you'll use the various of the different domain knowledge to explore the relationships in your data. And we'll start with measures of normality, whereby we'll look at graphical and statistical methods. We'll see at measures of central tendency, that's the mean and the median. And the mode, we'll look at measures of dispersion, the variance of the standard deviation, and the measures of relationships with the correlation and covariance. We start with measures of normality. When we are performing different statistical tests or machine learning algorithms, we are building some machine learning algorithms. There are different assumptions that we make, and one of the assumptions is that the data set follows Gaussian distribution of the data sets, or the data follows a normal distribution with a certain mean and certain standard deviation or variance. And in measures of normality, we use two methods, that's the statistical methods and the graphical method. We start off with the statistical methods, and in statistical method, we look at Kolmogorov's test and the Shapiro-Wilks test. And in both of these, we are testing a hypothesis. So we have to define our hypothesis and the null hypothesis in this statistical method, the Kolmogorov's test and the Shapiro-Wilks test, is that the data set is from normal distributed population, or the data set follows a Gaussian distribution, and the alternative hypothesis is that the data set is from a normal distribution, but it does not follow a Gaussian distribution. So we have to choose our alpha value. So our significance level, or our alpha level, we'll be using here, which is the default significance level, which is the 95% or 0.5% significance level. If the p-value is less than 0.05, we reject the null hypothesis. So we start with the Shapiro-Wilks test. I'm setting a random seed here to make the code reproducible. I'm creating data that follows a normal distribution. I'm using R-norm for normal, so R normal distribution, and I'm creating a data set called data_1 that follows a normal distribution, and the count, or the n, is 5. And that then I'm creating a data2 that follows an exponential function, and I'm saying data2, the number should be 10 and the rate is 2. And that, there it is. So I want to test if these two data sets follow normal distribution or not. Definitely this one, the first data follows a normal distribution, because you're created using the R-norm, and the RXP does not follow the normal distribution because it's an exponential, but we want to test it significantly at 95% confidence in significance level. I'm defining the hypothesis here. I'm saying the null hypothesis is that the data set follows the Gaussian distribution. What I mean is the data set is normal. And H1, I'm saying that the alternative hypothesis is that the data set follows non-Gaussian distribution. The data set is not normally distributed. If the p-value is less than 0.5, I reject the null hypothesis. What does that mean? If the p-value is less than 0.05, so if we reject this hypothesis, if we reject the null hypothesis, what does that mean? We reject this hypothesis and we conclude this other one. If we reject the null hypothesis, we have to conclude the alternative hypothesis. And if we fail to reject H naught or the null hypothesis, that means we conclude it. If we fail to reject it, definitely that means we accept it. So we conclude it. So Shapiro-Wilk test, we use Shapiro.test. We use Shapiro.test. Then you provide the name of the data or the data. So I'm saying Shapiro.test data _1 and that. And here is my p-value. My p-value is 0.06. So my p-value here, my p-value is 0.60. This 0.60 is greater than 0.05. So that means we fail to reject the null hypothesis. As a matter of fact, 0.060 actually is greater than 0.05. So this means that we fail to reject H naught. We fail to reject H naught. So we fail to reject this hypothesis. Sorry. We fail to reject H naught. So if we fail to reject it, that means we accept it. So we fail to reject H naught and conclude that the data set follows Gaussian distribution, or the data set is normally distributed. Let's do Shapiro.test for the second data set. Let's run this. Our p-value here is 2.629 times 10 raised to power 7. So that's 0.000002629. So this p-value is less than 0.05. So we reject H naught. So if we reject the null hypothesis, we reject this null hypothesis here, and we conclude that the data set does not follow Gaussian distribution. So that is it. Let's go to Kolmogorov's man of test, and here still our null hypothesis is that the data set is from normal distribution, and our alternative hypothesis is that this data set does not follow normal distribution. I'm creating a data called data 3, and I'm still using the R norm. I'm creating a normally distributed data. It's 300. Let's run that. Let's see the mean and the standard deviation of this data set. So I'm using the mean function, mean of the data _3, and the standard deviation. And it has a mean of 0.003. So this is approximately 0, and this one is approximately 1. I'm creating another data set called data _4, and it is exponential data. So the n is 300 and then the rate is 3. That. Now I want to test if this data set is normally distributed. I'm using ks.test. So this is for the Kolmogorov's man of test. We use ks.test, then the data, name of the data frame, then you say it's p norm. Oh yeah, you say p norm. Let's run that. Now our p value here is 0.2915. This value is greater than 0.05. This value here is greater than 0.05. So that means that we fail to reject the null hypothesis. So if we fail to reject this hypothesis, we fail to reject this hypothesis. So if we fail to reject it, that means we accept it. So we accept that the data set is from normal distribution. Let's this case the test data _4, and our p-value is this 2.2 times 10 raised to power negative 6. 0.0000, it's very small, so that means we reject the null hypothesis. So if we reject the null hypothesis, that means we accept the alternative. We reject this one, we reject H naught and conclude H naught. We conclude that the data set follows a normal distribution. Let's go into graphical methods to test for normality. And in graphical method, we use the histogram and the QQ plot. So in histogram, a data set that's normally distributed is roughly bell-shaped. So we will use the data set that we have created previously. That's the data 1, 2, 3, and 4. So here I'm creating I want to create we will use visualization. So here I want to create a 4-window pane. I want to plot 4 graphs in one pane. So I want the four graph to appear here. So I'm saying per mf row is equals to c. So that means 2 rows and 2 columns. So on that, then let me increase this one. Now I want to I'm using the function hist for histogram. So I want to create a histogram of data 1, and I'm saying color is equals to 3. So you can use 1, 2, 3, 4. Then the x lab, this is the x label, should be data 1. Let's run that. Let's see how it is. So this data set is roughly bell-shaped. It's roughly bell-shaped. So this the data 1 follows a normal distribution. Then the histogram of data 2, and I'm saying color is equals to 4. Here it is. This does not follow the normal distribution because it's not bell-shaped. So this data set is not normally distributed. Histogram of data 3, and here it is. This one is roughly normal. This one is roughly normal because it follows Gaussian distribution. Then data 4, here it is. This one is almost the same as this one. So as you can see, this per mf row has created this for it's created this one window for all this visualization, and you can as well zoom it. You can zoom. Here it is. It has been zoomed. Then if you want to return to the to plot one graph or one graph in this window, you use dev.off, and this returns you to that window. So that is the normal, or that is the histogram to test for normality. You can as well use the QQ plot. I'm still using the PRMF row. I run this, and if you want to use the QQ norm, you use the QQ norm to create the QQ plot. Now, if the points fall along a straight line, the data set is normally distributed. So I'm creating I want to plot this in one window. So I'll use PRMF022 on that. Then I run all this together. QQ norm of data 1, QQ norm of data 2, QQ norm of data 3, QQ norm of data 4. And here it is. So this one, the first one is normal because the data set follows roughly along a straight line. This one is not normal, so this one does not follow normal distribution. This one is normal, and this one is not normal. I'm using dev off again. That is measures of normality. Number 2, let's look at measures of central tendency. And the measures of central tendency are the mean, the mode, and the median. The mean, mode, and the median. And the mean is the average value of a given data set. So it is it's the summation of the observation divided by the number of the observation. Then median is the middle value when the data set is arranged either in ascending or descending order. That is the median. And the mode is the most appearing number. We use the function mean to calculate the mean certain observation or of vectors or yes, of vectors. Now here I'm saying the mean of empty cars and MPG. There is a data set called empty cars. So let's see head empty cars. This function head will give me the first 6 values of a data frame, and here it is. It has given me the head of them. So MPG, CYM, displacement. So what if I want the mean of MPG? So I'm using the function mean, then the name of the data frame, empty cars, and then the $sign. The $sign allows me to access a certain column. So I want MPG. Run that, and here it is. It gives me the mean of the vector MPG is 20.09062. So this is how you calculate the mean. The mean is the summation of the total observation divided by the total number. So this is how you calculate. You create a variable called sum, and you use the sum or summation function. You want the summation of the empty cars and the MPG column. Run that. So if you see what sum, use the summation. So it's 642.2. Now what does that mean? It is the summation of this entire column. I'm creating the count, or the count of empty cars. So I'm using the pipe operator here. So first of all, I have to load the package called tidyverse library. Tidyverse, so that it can allow you to access the pipe operator. And so I'm creating a count called n, and I'm saying empty cars. Then the pipe operator. The pipe operator is shift as control shift then m. What does that? What does this mean? It means that it's like saying and then. So I'm saying empty cars, then and then select. What do I want to select? I want to select MPG and then find the count of MPG. So run that. So what's the sum divided by n? Run that. It gives me the mean, which is 20.09062. Then there's a median. So you use the function median to calculate the median, and the median is 19.2. Let's look at the measures of dispersion. So dispersion is the spread or the deviation of the data from its average. So dispersion is the spread, or it's just the spread or the deviation of a data set from its mean or from its average position. So we look at variance and standard deviation. And what is variance? Variance is the average degree to which a variable deviates from its average. So average degree to which by how much value does a value, or by how much value does a certain vector deviates, or a certain value deviates from its mean. So it can be by certain value, this value moves from its mean. Then the standard deviation is the square root of variance. So you use VAR, variance, to calculate the variance. That's it. And here is the variance. The variance of the value or the variance of the MPG column in the empty cars data frame is 36.324. What does that mean? This means that the MPG column in the empty cars data frame deviates by this value. So it can either deviate positively from this value, or it can deviate negatively from this value. So this is what it means. It means that it can deviate positively. So that means you add this value to its variance, or you can less this value. by its variance. So here I'm saying I want to see the deviation, this is the positive deviation. So I want the variance of the MPG column in the data frame empty cast. So I'm summing plus its mean. I run that. So that is the positive deviation. So it can deviate by this value, the positive, and it can as well deviate from this value on the negative side. So this is the deviation. You use SD. One thing you need to know is that you cannot report the mean minus the variance. So the mean and the variance they go hand in hand. So the lower the variance, the better, the stable the estimate if you're using to estimate. And then the standard deviation, we use SD to calculate the standard deviation. So SD empty cast the MPG column. Run that. And finally, let's look at the measures of relationship. In the measures of relationships, looking at the correlation and covariance of a matrix. Covariance is a statistical term used to measure the direction of the linear relationship between variables, while correlation measures the direction and the strength. It measures both the direction and the strength of a linear relationship between variables. So both the correlation and covariance measures the relationship between various variables. So while covariance measures the direction, only the direction of linear relationship between variables, correlation measures the direction and the strength of linear relationship between variables. So correlation actually is a function of covariance. Correlation ranges from -1 to +1, and correlation can be easily measured because it has units, whereas covariance lacks unit. So you use cov for covariance in R. So I want the covariance, so I want to see the covariance or the relationship between MPG and the displacement in the empty cast data frame. So I'm saying covariance of the MPG column and the displacement column. Let's run that. This one gives me -63.0972. So what does this negative means? This negative means that they tend to move in an inverse direction. So if miles per gallon of this MPG increases, this displacement decreases, and if this increases, this other one decreases. That is what that means. Let's run this attach empty cars. What does the attach function does? The attach function, what does it? It allows you to access the columns of data frames without using the $sign. So I'm saying the correlation. So here I'm using correlation now. So this is I want to test the correlation. So the correlation of displacement and miles per gallon. So that it is. So the correlation is -0.84. So what does this negative means? This negative means that as one value increases, the other value increases. So and it is 0.8. So this means there is a strong positive relationship. There's a strong there's a strong negative relationship between displacement and miles per gallon, because it ranges from -1 to +1. So a positive -1 means a strong negative relationship, and +1 means a strong positive relationship. So the strength is strong because it's close to the value 1. You can as well find the correlation of an entire data frame. For example, I want to see the correlation of the entire empty cars data frame. So I run the correlation empty cars, and here it gives me the entire Let's run this again. Here it is the correlation of the entire data frame. You can as well use the covariance. There's a package called psych here, PSYCH, and this one allows you to perform the correlation of data frame, and it is accompanied by a beautiful visualization or beautiful graphs. See that it is I'm loading this library called psych. So if you don't have you have first of all to install the package using install.packages. I want to see the data frame called iris, so I'm saying head. I want to see a head, sorry for that. And here it is. So it has sepal length, sepal width, petal length, and the species. So I'm saying iris, and then I'm using the pipe operator. So iris, and then select everything in the iris except the species, then use pairs.panels function. So run this, see what it has given me. So the correlations between the sepal length and sepal load is negative 0.12. So there is a negative relationship. There is sepal length and petal length is 0.87. You continue until petal width and petal length is 0.96. So this is the beauty of the library psych. So basically that is the basic introduction to exploratory data analysis, whereby we have looked at measures of normality, measures of central tendency, measures of dispersion, and measures of relationship. Thank you. Enjoy learning.